Hello, everyone. We'll leave a couple of seconds for all the audience to come in. Welcome, everyone. So, the numbers are still growing, so we will wait for a couple of seconds. Now, wow, 40. Good audience today. Good numbers. I'm sure you'll be a good audience as well. So good morning, everyone, or good afternoon. It depends where you're based. It's good afternoon for me. So welcome to this NISQ webinar. It's actually the 7th webinar in our series of 9. We started in November. I'm Pascal Bernier-Bruna. I'm the communication leader for the NISQ project. And I will just share some practical information before I hand over to today's speakers. So this webinar is recorded and you will receive the link to the recording tomorrow. It is in listen-only mode because we have a lot of people registered, but you can ask your questions. You can use the Zoom Q&A panel to ask questions to the speakers and to see the questions asked by others, and you can upvote questions or comment on them. The chat is also open for more informal exchanges if you want. And that's about it for me. So I'm going to hand over to Dr. Venkatesh Kannan, who arranged this webinar and the other 3 in this series, and he will be our moderator today. Venkatesh, the floor is yours.
Thank you very much, Pascal, and welcome everyone to the webinar. It's good to see you all virtually joining us. So as Pascal mentioned, today's webinar, we have 2 speakers, Bob Coecke from Cambridge Quantum Computing and Antonio Villalpando from the NISQ project itself. So Bob currently works as the chief scientist in Cambridge Quantum, or Quantinuum, as they have rebranded themselves recently. He was previously a professor at the Oxford University, and he has been pioneering categorical quantum mechanics, ZX calculus, and the DiscoCat model for natural language processing, among many other things. So he is highly decorated and is very prominent in both the scientific community and as well as the wider media for his work. So it's a pleasure to welcome Bob joining us today to have his insights into quantum computing, particularly natural language processing. And following Bob, we'll have Antonio, who's currently working at the Irish Center for High-End Computing, and he works in the NISQ project, looking at developing methodologies for processing text data as a part of natural language processing use case. So welcome, Antonio. Thanks very much. So before we hand it over to Bob, maybe a quick overview of the NISQ project itself. So this is a project that started in September 2020. It's a 4-year project under the Quantum Flagship Program of the European Commission. It's basically composed of a partnership between enterprise and research organizations working on a set of practically relevant use cases. So if you could just move to the next slide, Pascal. Thank you. So the practical use cases within the NISQ project span the chemistry, machine learning and optimization, and the AI and graph algorithmic domains. So particularly this series of webinars that we have kicked off in February focuses on the AI and graph algorithmics methodologies. And as Pascal just said, this is a project among European entities, and it's driven by the European Quantum Flagship Program. So with that, I believe for your questions and answers, please keep sending them in as you have them in the Q&A session. And I hand over to Bob. Thank you very much.
Okay, thanks, Venkatesh. It's good to be here and meet again after a few years. I'm going to share my screen. That's this one. Share. Okay, here we are. So what I'm going to talk about today is, as was announced, quantum natural language processing, which is a fairly new field, but I'm also bringing this in a broader context of what we call compositional intelligence. So compositional intelligence is the name of my new team, now with Cambridge Quantum, but based in Oxford. So we are now starting to become quite a number of people. And so I'm going to give a little bit of an idea of the sort of things we are doing now, which very much QNLP is still the center, but the sort of ambition stretches a little bit beyond that. So let me start with a little bit of a discussion about NLP, like standard NLP, and what people call AI today. I really don't like the name AI, but okay, like when you know, a computer used to be a human, and then when the computers became machine, we didn't say artificial computers, we still say computers. So it's the same thing with intelligence. We shouldn't call it artificial. But anyway, so that's why we call it compositional intelligence. Like we dumb the word artificial and put something instead. So what do we know about AI today? There is incredible progress at the moment, and that's mainly due to the huge increase in computational power, which has gone up incredibly, especially since the use of GPUs, and also a huge increase in available data. We're talking about a factor of 1 million in 25 years or something like that, but actually much less a shift in a conceptual paradigm. One can argue that neural networks go back to the 1870s, and they were practically seen as a computational model since the 1940s. So it's really very much, it predates quantum mechanics, actually, the paradigm, and the other new things from the previous century, like relativity theory. Now, I also think that this lack of new paradigm also comes with a bunch of current shortcomings, which are very well known. And the most important one being the lack of interpretability, verifiability, safety, fairness, all these things come as a bit of a problem now. There's a humongous cost of data to it because it's all data driven. Computation is expensive. So the money needed to, for example, train GPT-3 is like 12 million in electricity alone. And it takes a lot of time, and then there is a really bad carbon footprint for doing anything like computation driven, of course. And another problem, which maybe people don't mention that much, but there is a lack of combinability with other successful computer science tools and methods. So computer science is not a failed area. You just have to look around and look at your mobile phone and the sort of pieces of software people can design now. There's a lot of tools and machinery which goes in there, and actually very little of that is used in the last 10, 15 years of AI. So what are the tools modern computer science deal with? And then like one of the main concepts there, the concept of compositionality. And compositionality, I'll explain what it is later. It gives you increased interpretability, verifiability, safety. It gives all the things you want. Composability of different tools and methods, that's just what it's all about. And writing software without it would simply be impossible today. You couldn't write an operating system or anything if you wouldn't use compositional principles. Now, I left a little line there because I want to emphasize that the sort of compositionality which is dominant in computer science is called Frege compositionality, which actually is not really due to Frege. People say it's due to Boole and some other people, but which says that the meaning of a whole is the meaning of the parts and the structure. And we know a lot of examples of that, like in language. One can say like that the meaning of a sentence arises from knowing the meaning of the words and the grammar. And that's why we don't really have dictionaries for sentences, and mainly only dictionaries for words, because you can derive the meaning of the sentence typically from the word meanings and its grammar. Anyway, that's sort of traditional view from linguistics. And the same is true for your software within a phone. These are like lots of little apps and lots of little things which interact with a well understood structure. Same is true for any CS applications. Mathematics works like this. You prove a few lemmas and then you structure them together in some way to prove a theorem. So this principle of compositionality is pretty much everywhere. However, modern machine working doesn't work like that. It's not that you basically tell the neurons what their meanings are, and then the neural network starts to sort of produce more complex things. It's kind of the other way around. You train the whole, and then the parts take meanings, but it's not really clear at all what these meanings are. It's kind of a black box. So that's what I'm writing here. And then another problem with modern machine learning is that GOFI, which stands for good old-fashioned AI structures, so things which people used to do and call AI before, they just don't fit together with the machine learning. And there are deep mathematical reasons for that. There are really deep mathematical reasons for that.
Sorry to interrupt,
yes?
Bob, but they cannot see. We cannot see part of your slides.
Oh, sorry. I'll do full screen. I forgot to do that. Enter full screen. Getting it all now?
Yes, I think so.
Yes. Yeah.
Yeah.
That's okay.
Thank you.
Yeah. It must have been just a little bit you're missing now.
Yes, it was just a little bit.
Because
I did not notice it at first, but
yeah,
some attendees
I
did.
I just noticed it myself now. so okay. So what is our prehistory here? So our prehistory goes back to in 2008, around 2008, at Oxford University, where I was then. So there were 3 people. One person knew about grammar algebra. Grammar algebra is sort of tools going back to people would mostly know Chomsky, and which tell you when a sentence is like grammatically well formed, or are to produce grammatically well formed sentences just using some algebra, some kind of algebra. So a little bit of explanation here, like you basically give some grammatical types to basic entities, like you would have something like a noun type, you would have something like a sentence type, and because they are sort of meaningful wholes. Now, a transitive verb or a verb typically is not that much of a meaningful whole, because in many cases you can't just use it to communicate. Basically, such a transitive verb would need an object and a subject, or to actually become a meaningful sentence. Like an example is like Alice hates Bob. Like the word hates doesn't really mean much in itself, but if you say Alice hates Bob, then suddenly the whole gets a meaning. And the way this algebra works is then by sort of assigning to something like a verb that needs something extra to become meaningful, to actually stick something on the left that's sort of inverse or negative, or you ever want to say that, something on the right, inverse or negative. And so here you see, if you then stick a subject on the left and a subject on the right, then they cancel out, and you actually compute the fact that you get a grammatical sentence of it. Like this sort of calculations, a nice thing about the recent generation of these calculations is that you can represent them diagrammatically. So the cancelling out of, say, the subject and the bit of the verb asking for a subject, you can sort of cancel them out, a bit like in physics in a field theory annihilation. And here, like the verb asking for the object, and then the providing the object also cancel out, and ultimately so you get the sentence type going through. So remember this simple little diagram here, which connects like a subject with part of the verb and the object with part of the verb, and then another part of the verb goes through. We're going to get back to that picture later. So somebody else who was then in Oxford, and now meanwhile also moved to Cambridge Quantum Continuum, was Steve Clark. He actually was at that time interested in vector space models, which are now, of course, everywhere, very prominent, but at the time they weren't as prominent as they are now. So they were still like in the early days exploring this paradigm. Me myself had nothing to do with linguistics whatsoever in a direct way. I was basically developing something which is called categorical quantum mechanics. And this is like drawing quantum mechanics pretty much in terms of pictures, but while retaining it as a purely mathematical formalism. So we produced this book some 5 years ago about this effort. And a bunch of the things in there are now using in quantum industry, especially ZX calculus, which came out of there in collaboration with Ross Duncan, who's the head of software at Cambridge Quantum and Continuum. So we developed ZX calculus. So there's a lot of stuff now in this book which is becoming increasingly relevant. But anyway, that's what I was doing. Now, when you produce these two stories together, a story about like the algebra of grammar, which you can refer to as compositional, and the vector space models of language, then a natural question is, how do you put the two together? How do you put the two together? We people, we know how to do this, of course, because if we know the meanings of words, then and the grammar, we can produce the meaning of a sentence. But can we make a machine do that? Like by understanding this grammatical structure, and this, can we combine them? And basically what happened actually a little bit before that was I was in 2004 in Montreal in McGill, and I was actually talking about categorical quantum mechanics. This was a category theory seminar in McGill. I say, okay, this is quantum teleportation. And then in the audience, there was somebody, Lambek. Lambek actually used, people would associate the name Chomsky mostly with the grammatical catcher. But Lambek is the person who actually did most of the mathematical work there. He was in the audience and he said, hey, Bob, this is grammar. So he saw me present quantum teleportation. He said, this is grammar. And this was a particular brand of grammar, which he called pre-groups, which he had introduced not too long before. So in a way, we had this picture on the left, which was teleportation, which on face value, but as Lambek identified, looks like grammar, but at the same time, it was about vectors, quantum states, vectors. So it was combining, in a way, meaning and grammar already. And if you thought about it a little bit, it kind of felt like the natural thing to do also for language. So we basically use this quantum formalism to model this interaction of meaning and grammar. And then this paper resulted, like the three of us, Mathematical Foundations for Compositional Distributional Model of Meaning. And the way it kind of works, I mean, you remember the picture, you remember the bottom here, this subject and verb combination, this object and verb combination, and then the sentence types going out, and you know the sentence a bit thicker. And then what you see here, basically, these are the meanings of the words. They are just a bunch of vectors, vector for Alice, vector for Aids, vector for Bob. And then this is the grammar, but we think of this as a linear map, just like in teleportation. Like, or this thing is actually a little bit like an inner product, this cup shape, it's like in a product. And so you can actually compute this thing. You can compute this thing, and this will give you a vector which you then represent as the meaning of a sentence. And then you can do things like, for example, take inner product of different sentences, like Alice hates Bob, and Alice does not like Bob. You expect these meanings to be closely related, so you expect the value of this inner product to be quite high. Just think of it as a Born rule. You can just take the moduli square of like how you quantum mechanics, you compute like a closeness or measurement likeliness stuff. You can think of this like that. This got a lot of attention at the time. This got quite a bit of attention because it was kind of an open theoretical problem which we solved. Of course, what happened immediately after was the big AI boom. Boom! Just a big boom. Everybody started to do AI because of all this increased power. And so all these methods, of course, they did a lot of, they've changed society now, meanwhile. They've changed society. You can't deny that. So what I must show here is what were the advantages of this Coecke, which is how the formalism is now known then. So I'm talking 2010, and where NLP and A is now. So there are advantages to both. There are advantages to the compositional formalism we have. There are advantages, of course, to AI as it is now. I'm not going to go through the list. I'm happy to explain offline or something the meaning of all these things, but it's like a comparative table of the two formalisms now. So they both have their advantages as it stands now. Okay, now I'm going to work towards something that we hope takes up the best of both worlds. We call these language circuits. Actually, now we call them text circuits. And this kind of started in a paper which I wrote a few years ago, which is called The Mathematics of Text Structure. So what we did in there is we used some other tools. So far, I've been showing you wires. So these wires came out of categorical quantum mechanics, but if you open the book, let me show it. I don't have it. So the book which I showed earlier with Alex Kissinger, with a little dodo on the front, then you'll see that a lot of this book is about something we call spiders. And spiders are some generalization of the notion of wire. So if you got two wires and you put them together, then you get one long piece of wire. That's what you do with wire. If you take two pieces of wire or like electricity cables, you can plug them together and you get a long electricity cable. So this is a spider. So this is a wire with multiple inputs and outputs. You kind of can think of it as, how is it called, like a socket in which you can put multiple plugs and stuff like that. The result is that anything you plug together will just be connected to the net, to the electricity. So we'll all be connected together. So in that way, you can think of this like going from a straight extension lead to a socket with multiple plugs. And so we call these things spiders. And the only rule they have is that they fuse together in one hole. That's the way to think about it, like everything being connected. And then what we did next is we for actually very justified reason, we think that the verb has some internal structure with two spiders there. And then we just pull this out. So we get sort of a, so this was the picture before where these two wires in the middle was the sentence type, representing an object and a subject. And by sticking these two spiders in there, we get this picture. So the way we think about this now is you got Alice and you got Bob as two actors in your story. And what the verb does, it sort of connects them together. It sort of says, now there is a new relationship or an entanglement, if you want, between Alice and Bob, in the sense that there is a hate relation between them. So it's sort of a different representation of the way we were thinking before. And the real upshot comes about when you start composing sentences. Like, for example, you can have Alice hates Bob and Bob likes beer. And this can go on forever. You can see that you can introduce more people, you can introduce more verbs. Now, this is, of course, very simple sentences, but in a paper which we'll publicize soon, we extend this to all of English, this new circuit form of language. So it's a new form. While Discoquette was just about sentences, this is about text, and it has a lot of other advantages. I'm not going to go to all of them, but so one of the nice advantages is as opposed to modern AI is like meanings evolve. So GPT-3 was once trained and basically everything had a fixed meaning. Here, the meaning of Alice and Bob in our pictures, they will evolve due to the events that occur. They might get married, they might divorce, they might get kids. So clearly the meanings are changing. Alice becomes a mother, Bob becomes a father. So we got these evolving meanings, which I think is an interesting feature. Something I can't go into too much detail in because this is a talk in its own right. But basically, while the grammatical gadgets, not in their abstract structure, but in their concrete structure, are language dependent because the order of words is different in different languages, this circuit lose these language dependencies. So are in a way a more universal representation in language, which abstract away specific choices of word order which are made in different language. And it's abstracts away some more sort of subjective structure of language. So it's a much more compact, simple representation of meaning. Basically, so this is a different piece of grammar. This is sort of Chomsky-like generative grammar, but a complex thing like this becomes a simple circuit like this, which can very easily remember. So like I said, it's kind of a talk in its own right. It's much more interpretable, verifiable, safer, all the good stuff you want. It's much cheaper, and it combines the best of both worlds, of AI. One nice thing is, we've got this book on quantum mechanics, which we use some inspiration for initially, but it actually gives a full logical framework to now reason about language if we're going to go full on with this quantum diagrammatic formalism. A fairly recent result, it's now dating back to 2007, is actually these people here, they have proved that any reasoning you can do in Hilbert space, equational reasoning, you can actually do with the categorical quantum mechanics as in this book. So it's a full-blown, complete logical system. And this is where I think that we can bring back logic and reasoning into AI or whatever you want to call it. But it is a different type of mathematics than traditional propositional AI reasoning structures. It's this, but this category of quantum mechanics, I think, should now be taken seriously as a reasoning structure for AI. That's what we're doing. Okay, my table. Go back to my table. So the way we see it is that we've now got a formalism in which we can get the best of both worlds. Both what Discoquette was bringing, both what AI is now doing, and more stuff. There's some more new stuff which neither of those had. Anyway, this is only the beginning. But, so there's a big but to all of this. So this was all a very nice story, but nothing comes for free. Doing this stuff is exponentially expensive. That's a big problem. So if you want to do all this stuff on a classical machine, you're going to get in trouble soon. I mean, we're doing it, we're trying it, but you're going to get in trouble probably. And you have to do a lot of hacking. So basically what you do is, well, I mean, this is actually already an idea which came up in 2016 with Will Zhang, to actually just do it on a quantum computer. So what we did in this, so the natural thing is stick it on a quantum computer, and the next question you ask is, do you get additional advantages doing that? Algorithmic advantages. And in that paper, Will and I, we said, yes, you get some Google-like speedups for a very standard NLP task. So you get a speedup. It's a Groover style, it's Groover-like, so it's not exponential, but you do get a speedup. Okay, so we can also add a line about quantum speedup to our table. Okay, but this was just theory. Then we actually quantum computers had grown a bit, so he actually wanted to do this practically. Now, I can't go into too much details, but we're in the NISQ area, and the NISQ area is not the ideological quantum computer from 10 years ago. In particular, it's really hard to get data on your quantum computer, so you have to come up with different tricks to get stuff practically on your quantum computer, which we developed in this paper. And basically, so what we actually have to do is also turn this into a quantum circuit. So we're now using this ICHEC calculus. This is just using the ICHEC calculus to actually turn this sentence in a quantum circuit, and you parameterize it. And then we use the paradigm of, I can't go in detail on variational circuits, but then you use the paradigm of variational circuits to get your data inside, to train your meanings of words on the quantum computer. And basically we did the experiments, we got good results. We then did bigger experiments, we got good results. We're now doing even bigger experiments practically. We got a big team to do that. And what we have done is, like all the software we have developed in the way, we actually packaged this in a nice way, and we made this freely available as an open source software to the world. So everybody can now do quantum natural language processing using this software package which we developed. We've got a Discord server to help people do so. Just mail me either on LinkedIn or Twitter or whatever, and we can provide you with a link so that you can get sort of guided participation in this effort. Okay, I just want to say one last thing before I stop. So anyway, just go there, use this stuff, play around with it. Everybody can do it. Okay, so far I mentioned very little about quantum algorithms, just like the old work from 5 years ago with Will Zhang, where we came up with some Groover-like speed up for like classification tasks or some question answering, naive question answering like stuff. Now, how do we see the algorithms here really go forward? And the way we think now is the best sort of probably one of the most promising things in quantum computing as a whole is to actually potentially get exponential speed ups by thinking of natural language as a quantum process which you then simulate. So basically, as most people know, the start of quantum computing to some extent was Richard Feynman saying, like, if you got a quantum system and you're going to simulate it on a machine, then your machine better be a quantum computer, because otherwise it's going to be very complex. Really, because of the blow up in the size due to the tensors, as one thing. That's one thing, but there's actually, of course, more problems that go on. And what we do now is we really think of our text, like I presented these text circuits, like where text progresses. They are a piece of text, and you can think of this as quantum evolution. Just like you can think of your chemical evolution in quantum chemistry to be like a process. Basically, in chemistry, you got the Hamiltonian dictating what goes on. Here we got something that you could call text to circuit, which dictates what's really going on. So we're working towards experiments now. We've done the theoretical analysis for all of that. We're working towards experiments, and the idea is then to basically reap all the advantages you could get from quantum chemistry, but actually within natural language, textual natural language processing. So we really think that, and people talk about exponential. I even saw talk about doubly exponential in quantum chemistry. So that's sort of what we're now trying to chase algorithmically. I think I'm running out of time, right?
You can take even 5 minutes, Rob.
Oh, that's okay. I'll just need 1 or 2 minutes, so
sure, please.
Can leave the rest for questions. So basically here is the full table. We got a lot of promise now, I think, to what we're doing for this like textual natural language processing, and there's of course the quantum speed up, which is a big promise now. Okay, so far this was mostly about language, while I tried to build a bigger picture earlier on with starting with a story about AI. And so that's where we see compositional intelligence. So this NLP story, which I just told, is an instance of what I would call compositional intelligence. Now, we've done so far we only talk about language, but there is actually many other structures which are relevant to us being humans, as us being like an intelligence being, and some of the lessons we learned in earlier generations of AI was the importance of embodiment, for example, that intelligence has so much to do with actually being a body that lives in a world that interacts with other things, such an important part of intelligence. So, and this can be related to observing colors, to tasting, to smelling, to moving around in physical space, things like that. And so we start to explore these structures also a while back to see whether the same sort of reasoning mechanism which we just showed in the case of natural language can actually be used to these more interesting spaces in a way, because we were just using these statistical vector spaces, and these are sort of more conceptually informed spaces. So we've been working on this. We also did the same for physical space. Physical space, of course, very important space in which we live. We observe it and we move around in it. So we sort of extended all our diagrammatic reasoning to physical space. Here is the example of a chess piece. So we now, for example, have semantics for some sentence like the pawn next to the king that a knight might capture. I mean, this is not stuff you figure out empirically necessarily. You can basically just encode this just as a model and then do grammatical reasoning about like a chess game, and really. So that's the sort of things we have been developing. But at the same time, Steve Clark and his team here in Oxford in our CQ team, they're now also trying to sort of learn these structures to really go to some form of AI that goes beyond just language and as all these other conceptual spaces. I mean, you can mix up language, for example. So you've got a space. I mean, you've got a spatial story, and then you've got some other stories. And the cheese inside the suitcase steaks is where you got, for example, interaction of different conceptual modes. Another thing we did was basically we started to generate music with these structures to, again, show that it's not just about language. And the remarkable thing which happened there is that we actually ended up in #1 in some classical charts with a song, well, a piece of music that was basically generated by means of quantum computing. So it was kind of a really cool thing. Okay, yes, I think I end here now. I'm not going to give a conclusion. I mean, I publicize a lot about this work on Twitter. If you're interested to follow, then you can do that. Okay, I'm going to end up here then.
Brilliant. That was really interesting. Thank you very much, Bob. We have quite a few questions. We can definitely come to them once Antonio also finishes. But thanks very much. Next, we have Antonio from NISQ presenting on processing text with quantum computers. Over to you, Antonio.
Okay, thank you very much, Venkatesh, and thank you, Bob, for this interesting talk. It was a pleasure to hear. And yeah, let me share my screen. Okay, I think that I have to stop Bob's screen. Yeah. Okay, so let's go back. Can you see the screen properly, or?
Yeah, we have just went through all your presentation there.
Yeah, sorry for that.
Thanks, Antonio.
But it is full screen and everything is okay, right?
Good, yeah.
Okay. Okay, so as Bob has talked about the DISCO-CAT model and he's the best person to talk about it, I thought that my talk could be about a little bit different things. So we are going to cover some NLP classical algorithms and review what people are trying to do to transform that into quantum algorithms. Okay, so moving on, first slide about what is NLP. As I'm sure that all of you already know, but it is a branch of artificial intelligence. I know that Bob's just said that the wording is not the best, but that's how people call it. And it allows computers to understand, analyze, and respond to natural language. And some task that we try to solve using NLP is named entity recognition or topic classification or machine translation or question answering. I mean, there are a lot of things you can do with raw data after processing it and retrieving information from it. So a quick timeline about the NLP. A huge event in NLP was in the 50s when the Georgetown experiment was done. It was a very influential demonstration of machine translation by IBM. Then you have also the grammar theories by Lambeck and Chomsky in the 50s and the proposition of the Turing test. Then in the 60s, we have some bots that worked on restricted vocabulary natural language understanding programs. Then in the 70s, we have some chatbots and conceptual ontologies. In the 80s and in the 90s, the first algorithms using machine learning were used with statistical models and decision trees. Then the neural networks were widely used in NLP, although they were proposed a lot of years earlier. And then in this last decade, a huge improvement in NLP was made with the use of word-to-vec. That is a neural network model to learn word associations from a large corpus of text. And once trained, the model can detect synonymous words or suggest additional words for a partial sentence. Then we have Globe that was introduced in 2014. That is an unsupervised learning algorithm for obtaining vector representation for words. And we also have the introduction of sequence-to-sequence models like recurrent networks, long short-term memories, or gated recurrent units. Then 2017 was a very important year for NLP with the introduction of the transformer. And it is a sequence-to-sequence model, but they added this attention layer that allows to process all the data in parallel. And then in 2018, we have some complex models that, for word embeddings like BERT or ELMO that are based in the transformer architecture and are unsupervised models that are later used in supervised learning for fine-tuning. And in the recent years, we have attention alternatives because the attention mechanism is not very efficient. So they are looking for ways to switch the attention layer by linear layers or Fourier transforms or something like that. So we now see how a common classical NLP pipeline is. You first have the tokenizer that it will segment the text and create an object with the discovered segment boundaries. Then you have some tagging that will predict the part of a speech of those tokens. And then you have a parsing that will detect the syntactic dependency of the different tokens. So once you have the tokens, you parameterize them into using hot-one encoding. That's the most naive way to do it, or dense vectors like word-to-vec, or context-dependent models like BERT or ELMO. And one common thing to do in NLP is to use transfer learning, where you use pre-trained models and you drop the last layers to use that model into another task that can be supervised learning, and you change your parameters in using fine-tuning. Okay, so when we now to quantum machine learning, what you're trying to do is to have quantum circuits that have some free parameters and you want to discover which are the values of those parameters that are able to somehow give you information about what you're trying to modelize. So first you need an ansatz. The ansatz is the subroutine that is consisting of a sequence of gates that are applied to specific wires in your circuit. Usually they are compared to neural networks, but the comparison is not very good in my opinion. And it defines the base structures and with the types of gates and the order of these gates that you have to apply to your qubits. There are many variational circuits ansatz that have been proposed by the community, and depending on the field, for example, you have ansatz for a graph optimization or for quantum chemistry, and the strength of that ansatz will depend on the desired use case. Normally, you can distinguish between 3 different base structures for your ansatz that are layered gate ansatz or alternating operator ansatz, or an ansatz that will reproduce a tensor network structure like matrix product states. After that, you want to define your parameterized quantum circuit that will depend on some free parameters, and then you define an observable for a qubit or a set of qubit that can commonly the expectation value of that observable is used, but you can create classical functions to post-process the output of your quantum circuit and change the parameter of that circuit based on a classical optimizer. And to train your circuit, you can use gradient-based optimizers or gradient-free stochastic optimizers. And you can also use quantum natural gradient or differentiable quantum circuits. And okay, so let's talk about the experiment that we did using this Coecke diagram. This was to reproduce what the group from Bob is doing. So you have a set of words that you will try to encode using 3 parameters. And with those words, you construct sentences, and you can build a diagram for those sentences. Here you can see an example. So if you see the blue dashed line, at the left of that line, you have the word embeddings, and on the right, you have the compositional grammars, the caps that were shown in the diagrams in the previous talk. So if you measure the qubit carrying the sentence information, you have some measurement between 0 and 1 that you can use to train a model. That's what we did. We used a data set concerning the animal kingdom with several sentence structures, and they are classified as true or false. And for each word, we use the cross entropy because we are looking into binary classification, and then you calculate the loss function for the whole data set. So this was before Lambeck was released. So what we were trying to do here is reproducing the result of his group. And yeah, we did it. We used the Covilla optimizer as the classical optimizer, and we were able to classify those sentences as true or false. Although for the test data set, the results were not as good. So we believe that in our model, we had some kind of overfitting. And with the training of those embeddings, we also made another task that was having sentences without some words and letting the algorithm decide which is the best fitting word in that for that incomplete sentence. So you can see here the probability of each sentence being true. And you can see that, for example, on the left, cat eats fish is the best fitting. I mean, fish. Sorry, cat is the best word for that sentence. But on the right, you can see that although we get the right sentence, dog eats bone, we also get very high value for dog eats seed that makes no sense actually. So we still have to work on that. Okay, so we are now going to talk about some classical NLP algorithms and see some suggestion about the community to build a quantum version of them. One of them is they are sequence-to-sequence models, and these models will take as input a sequence and will output another sequence, and in the middle you get hidden states, and the information will propagate between the nodes of that network. So the most simple cell that you can have is the recurrent network. So you see here a wire coming from the left. That's the hidden state from the previous step. And then you have below the input of, the input of the sequence. You have an activation function and you output. You have the output and the hidden state for the next cell. There are some evolution, like the long short-term memory and the gate recurrent unit. For example, the long short-term memory that you see in the middle is composed of a cell, an input gate, and an output gate, and a forget gate. So the input gate is here below. You have also the hidden state from the previous cell. This first sigmoid that you see here is the forget gate. So the good thing about the long short-term memory is that they are well suited to classify, processing, and making prediction based on time series data, since they can retrieve information for previous states of your sequence. And they were developed to deal with the vanishing gradient that is very common in recurrent networks. And in 2019, for example, it was used to create AlphaStart, that was a deep learning model that was able to beat some pro players at StarCraft 2. So it is not only used in NLP. So in the quantum realm, we find that a quantum version of the long short-term memory has been proposed. And what they do is to replace the feed-forward neural networks with quantum circuits, as you see in the image below. And also, there are some propositions about using recurrent arithmetic circuits that are modification of recurrent networks. They only differ in the activation function, and they are mapped to matrix product states. So you can find in the literature that a single layer recurrent arithmetic circuit can be mapped to a matrix product state. And studying this circuit, the analysis of learning in recurrent networks for temporal data can be performed from the many-body quantum physics perspective. And for instance, one can compute the entanglement entropy of the matrix product states, which can be thought like a measurement of the amount of temporal correlation that can be supported by that network. So the larger the entanglement entropy is, the larger the entanglement entropy means that the output of the network depends on the temporal data in the past. So this enabled the network to have some kind of memory. We can talk also about quantum neurons. They are like building blocks for quantum networks, like in classical neural networks, and they are able to process entangled states and add some nonlinear activation function that we don't find that in regular variational quantum circuits. So there are also some implementation of quantum recurrent neural networks, and that can be used to add some nonlinear activation for the output, for example, of the DiscoCAT circuit. And you can also find in the literature that tensor state, like matrix product state and matrix product operators, can be used to reduce and simplify recurrent neural networks. And we can also talk about the transformer. The transformer is a model that's able to capture a relationship between words and sequence of words. And the good thing of the transformer is that it offers a grid parallelization with respect to other sequence-to-sequence models. So the transformer block is characterized by a multi-head self-attention mechanism that you can see here in the picture, but it is not very efficient, and it is quadratic in the size of the data set. In the transformer, you need to have your input, and then you need to add some input, some positional encoding. And then you apply the multi-head attention layer that is followed by some normalization and feed-forward layers. And the attention mechanism, you can find it in this formula here. For each token, you have a query vector, a key vector, and a value vectors. Those are the Q, K, and V that you see in the formula. So what you do is that you calculate the product between the query and the key, you normalize, and then you apply a softmax, and that gives you a set of weights that you then apply to your value. So you can calculate the compatibility between the different tokens of your sequence. And then you go through a decoder layer on the left, and as a result, you start with a set of inputs, a sequence, and then you end up with another sequence that will be the output of the transformer. So some proposition about creating a quantum transformer can be found in the literature. For example, in this paper here, they replaced the Q, K, and V matrices with quantum operators that you can train with variational quantum circuits. But some questions are open, like if quantum computing can offer a better positional encoding, because you can use the entanglement to reflect the relationship between the different words in your sentence in a deeper way than classical algorithms could. And also there is this open question about if there is a quantum alternative to attention, because attention is quadratic on the size of the document, and some propositions have been made to replace this layer. There are many alternatives that you can find in this table. And for example, this picture here tries to replace the attention mechanism by a Fourier transform, and quantum computers are very efficient in implementing certain transforms like the Fourier transform or the discrete cosine transform. So it is worth investigating if some different kernel can be used in a transformer-like architecture. Another interesting thing that we could use for quantum NLP are dressed quantum circuits. They are hybrid models that incorporate the classical neural network as pre-processing and post-processing layers for quantum circuits. The idea here is to use dimensionality reduction to reuse classical pre-trained embeddings. So this will allow to use existing models like BERT for quantum circuits. So the idea is that you have this quantum circuit Q with a hat. that is composed of a classical pre-processing, the quantum circuit itself, and some classical post-processing. And the quantum circuit in the middle is composed of embedding layer, the evolution of the system U, and the measurement M. And this has been previously used in image classification by the team in Xanadu. And we wonder if this is worth investigating. So we are also proposing some architecture that this is just a naive implementation, but we are thinking about using some neural network to, this is a high dimensional classical word embedding, and then we can feed a neural network to get a lower dimensional parameters that we can use as a first input for the parameters of the NISQ model. And we need to train the weights of this neural network to actually reflect the similarity between the words of the classical embeddings into the quantum embeddings. Then we would write the NISQ quantum circuit. And one of the overhead that the NISQ model has, in my opinion, is that you have to perform post-processing. And we wonder if it is possible to implement some amplitude amplification, so you only get the states that you are interested in, because you have some projection to the zero state in all the qubits except those carrying the same.
Oh, it seems we have a problem. Antonio suddenly disappeared. I'm sorry for this. Venkatesh, can you maybe take over and start the question, the Q&A session, while Antonio is probably trying to to join us again? Venkatesh? No, we haven't lost him as well. Why? We've lost him too. Well, maybe they. Oh, here is. They probably have a problem. They are probably on the same location, so maybe they had some kind of connection problem. Sorry for this.
Sorry about that. I'm back now. I realized Antonio dropped off a few moments ago as well.
Yeah. So I was saying, I don't know why. I mean, maybe do you have a connection problem? Are you on the same location, on the same site, Antonio and you?
Just probably the same city, but no, not the same location. Yeah.
I thought maybe we can we start the Q&A session while we wait for Antonio to come back. Hope he can come back.
Absolutely, that'll be a good idea.
We had lots of questions, and Bob has been extremely busy typing answers. So, but maybe you want to comment on some of the questions, Bob or Venkatesh? So we have 11 questions that have already been answered, but
I think Antonio just joined us.
Oh, here is Antonio. Hello, Antonio. We can't see you yet, can't hear you yet, but.
Hi, hello.
Hi.
Hi. Sorry, my internet connection just died, so I am connecting through my mobile phone.
Oh.
But it was just the final slide. Just I wanted to explain that diagram, so I can quickly do that. I mean, we were at the output of the NISQ model after the classical neural network to reduce the size of the classical word embeddings, and the idea was to use amplitude amplification to get the state that we are interested in the DiscoCAT model to reduce the overhead of post-selection. And then we could implement some neural networks that we introduced in a previous slide to implement non-linear activation functions, because the good thing about the neural network architecture is that you can implement this non-linear function, but you are processing the state in superposition. So that's a very good thing, that in contrast to creating a classical function for post-processing. So in that sense, we can get the output of the DiscoCAT circuits and create like a richer embedding for the sentences. And given two embeddings, I mean, two sentences with this richer embedding, we can create another operator that is trainable, that will be a mesh, a distance operator. So with that information, we could implement some topic classification or some unsupervised learning algorithms like a k-means or a random forest to perform clustering with sentences. Another option would be to use the universal sentence encoder that Google has released as the label of the sentences, and use this algorithm in a supervised learning fashion. So that was everything that I wanted to say for that final slide. I'm sorry that you can't see it because I can't share the slides from my phone. And yeah, that was me. Thank you very much for your attention.
Thank you, Antonio.
Thank you very much, Antonio. And I believe, as Pascal pointed out, Bob, you had been answering many of the questions. So is there anything in particular that you would like to comment in addition to your answers?
Can you repeat, Venkatesh?
Oh, I was also asking. Bob.
Yeah, I was on mute. So it was the point where maybe there was some confusion when people thought I described DiscoCAT as Phrygian. So the main issue there, initially we were thinking along these terms. We were thinking, okay, you get the meaning from the whole from the meaning of the parts. That was just how it was set up. And that's the way we were thinking about it. Per se, the way I see Phrygian has nothing to do with propositional or true false, because it can take any sort of data, vectors or whatever. It doesn't matter. It's just a bottom-up thing. Now, one of the things we of course learned, and which is part of the success of stochastic NLP, is that a lot of meanings go top-down too. Like in many cases, the context really changes the meaning of the words. And in traditional linguistics, people thought these are exceptional cases, but it turns out that this is much more standard now than it was. But in the model which we had, DiscoCAT didn't really depend on, we use it as a paradigm, but it was not necessary. And then we were forced to do actually things on a quantum computer using variational algorithms. We're basically defining the meanings of words within their broader context, because you get like a big circuit, which is sentence or text, and then the meanings of the words are trained within this bigger context. So it's much more top-down. And these diagrammatic formalisms, I think they are by default post-Frege mathematics. You don't say what are the structures which flow in the wires. You don't have to say whether the small informs the large or the large informs the small. It doesn't matter. It's just like you got connections between the different layers of specification. And yeah, I think it's a new paradigm in itself as a new paradigm of compositionality, because sort of bottom-up thing is going to break down in a lot of places. In many cases, the sort of interactions are actually more important than the individual descriptions. When we talk about social structures, it's not just about knowing which people participate. Usually the structures are more communal than they actually come from the particular meaning of a person. So I think there's a big future more broadly in this sort of compositional post-Frege mathematics, which needs to be much better understood. So that's sort of an intellectual academic comment on one of the questions.
Thank you very much. So let's have, I'm just passing through the remaining questions there. So one question from Jonas. So it's basically a question asking if there is a short or intuitive answer for how a quantum computer.
Yes, I mean it's really in the basics of the way quantum mechanics deals with composite systems. If you combine two systems, you use the tensor product, and this means that you basically multiply the new basis, the multiplication of the size of the two existing bases, rather than what you would have expected maybe classically, that it is the sum. And so you get this. So if you got two, more intuitively, if you got two quantum systems, the space of states of the two systems is not the states of one system paired with the states of the other. It's the space of all functions from one system to another, which is much larger, of course. And that's where the exponential blow up of space happens. But in this particular, I mean, so for chemistry and all that is problematic, like the sort of size of chemicals that you can simulate on a classical machine is pretty small. Like even a coffee molecule is really hard to do on a classical machine, specifically because of this blow up. Now we take this as an advantage because the models of interaction in language and probably other systems, interaction models, they naturally have this mapping spaces rather than just spaces describing the individuals. And so that's the way we see it, is these things are sort of quantum native, because you got these functional spaces between everything, and classically it's going to blow up, but quantumly it sort of fits naturally, because quantum naturally has these function spaces between systems. Is that clear? Yeah, this question, coffee molecules. Yeah, I mean, for a lot of chemical applications, you want to actually understand how the chemical works, how it behaves. Experiments with a new chemical can, and for example, in healthcare, can go on for 10 years in order to actually understand this. If you're really going to learn these things purely by experiments, so people want to try to understand chemicals, the molecules, in a more theoretical way. And that's where classical computers just can't deal with it. It's too complicated. And it the way, I mean, at the moment, quantum computing is pretty much on par. It's equal with what you can do classically, given the current machines. So it's not going to take very long before it takes over. The analogy I was pushing is that one needs to think of language also as an evolution, so that the same sort of story applies there.
Could you comment, Bob, on naturally one of the primary remaining challenges, which is, you mentioned briefly, the challenge is getting actually the data encoded, basically, rather than the formalism in which it is actually represented and processed.
Can you say again?
One of the primary remaining challenges in having smart ways to efficiently encode data to reduce that cost, rather than the formalism itself to represent the data and to do the processing. So could you comment a bit on smart methods which are used to kind of encode different kind of data, at least within the context of text or natural language processing?
Well, I mean, at the moment we've been pretty brute force with these things. We just used plain DiscoCat or DiscoCirc, like we say, without any more fuss, to see, can we just get something to work like this? And as you know, it worked. And I think a lot of people would have been surprised at the time that we could actually do anything with NLP on a quantum computer. Of course, now we got a larger development. So the question is, when do you want to start using smart tricks? At which point? You don't want to sort of immediately develop something which is a little bit sort of confused and obscure, and that you actually lose track of what is the essence of where you get your advantage. So I'm big very much in favor of trying to do things as pure as possible, as long as possible. But of course, all the available tricks are there. So you could in principle use it. So we are mainly now exploring things in a clean way and how far we can get with it. Although we are looking into attention mechanisms and all that too, and how attention mechanisms naturally fit on a quantum computer. I mean, the papers there's no papers out yet on that, but we're looking at, and of course, all the other tricks too. But then, for example, in the case of attention, we want to see, can we cast attention in a very quantum native way, or a naturally compositional way, so that it all fits nicely together. So we're trying to stay pretty academic on that sort of front.
Sure. And one more question is about DNA compositionality in terms of genetics as a language. Any thoughts that you might have on it?
Excuse me, where is the question?
From Emil Dimitrov, DNA compositionality.
Oh, DNA. So that's interesting. So yeah, we're actually working now. I can't really say the names yet because it's not official, but we're working with two big medical companies now to see to which extent the NLP methods can also be useful there directly in the sort of DNA type grammatical structure and all that. It's a very natural thing. I mean, it's very similar to what we did with the music, because there's also grammars for musical composition, and there's grammars in DNA stuff, and we expect them to all be part of the same big family of applications.
Right. And I
mean, I mean, I don't know much about it myself. I mean, I know a bit of music, I know very little about like DNA grammar, so we will be hiring people specifically for that, of course.
And Bob, regarding a couple of questions in the chat about if you can reuse the same quantum circuit for multiple words, and about how many parameters do you need, and if you somehow memorize the parameters for each word. That's actually a problem that we also are facing about, for example, if you let Lambeck decide the diagram for a couple of sentences, namely, I am here and here I am, it will return different wires and different categories for those words. For example, the verb in the first example will have 3 wires, and in the second example, you will have more wires with different categories. So if you have a set of parameters that you have trained and you face this same word in a different context that is required to have more parameters, how do you face that?
Okay, I think there's a few different questions here together with different answers. So first of all, like the 2 sentences you mentioned, we kind of meant the same, but actually are different when you say them. When you move to the circuit formalism, they become the same. They become the same. All these differences get abstracted away. We call this the bureaucracy of language, of us humans only being able to speak in 1 dimension. So since we words naturally don't want to live in a line; they want to live in a plane. And when you go to this planar representation, then actually all these differences vanish. Of course, then the other question is how meaning can, when the contexts are generally different in meaning, of course, meanings can be very different. I mean, I said this in the previous comment, we've learned that for modern NLP, this becomes very important. Of course, if you look at GPT-3, they all have static meanings anyway. They just have each word as one meaning, and you can just stick to it. Now, to actually move between different grammatical uses, for example, you can have red as a noun, you can have red as an adjective. You can have, and then for some things, they actually lift to the level of verb. They can be both a noun, an adjective, and a verb. So we basically use always the same trick, which are these internal wirings, these spiders and all that, to basically change the type of things. I mean, there's some more research need to be done, but we've consistently been using this sort of spiders to move between like the different grammatical categories for things which actually naturally move between. I mean, I use this at some point to sort of reduce the, and again, this all becomes much more natural in the text representation of meaning. if I've got, so think about, you can think of red as a state, like a triangle. And then if I use a spider, it suddenly becomes an adjective, a box. And
Yeah,
so on.
that makes sense. Yeah. And also,
I mean, the main problem there,
yeah.
the main problem there is that so far we mostly used always the same spiders, which are basis dependent. So you really want to introduce an extra variable there, like a change of basis, to actually make sure that they don't always commute, because you don't want these things to commute.
Yeah. Sure. Yeah, and you mentioned GPT-3, and you said that the embeddings are static, but you have this positional encoding where it will change the values of your embeddings depending on the context of that word. So what
Sure,
are your thoughts?
Sure, but that's like saying that the word depends on the context in which it's used is kind of different than the meaning evolving over time.
Sure.
As events happen. So they're two different things. They're two different things, I would say. I mean, for example, if you train, I mean, GPT-3 was initially trained before COVID. So for GPT-3, COVID didn't exist. And the world changed a lot, and we all changed a lot, and our meanings changed a lot. But it was not anticipated. So that's what I'm talking about.
Yeah, but my question was, yeah, I mean, I understand that what you mean about the meanings evolving, and that's very nice because you can take a book and train the NISQ model on a book, and it will, I mean, the meanings will evolve,
yeah,
have the character change, and yeah.
Yes, it's more that story. Sure. It's two different things. Like, I mean, of course, you got entries in dictionaries which haven't changed much in recent years. Like the meaning of Napoleon hasn't changed much in recent years. But if you're talking about an evolving story with characters, then of course the point is that meanings change all over the time. If you think of some sort of detective story, then you're continuously changing the meaning as the story evolves, and then you'll figure out who's the murderer by the end, by these changing meanings. So I think it's different. It's a different application range for those where you deal with changing meaning, and those where you just accept meanings to be pretty static. It's a different scope for potential applications.
Yeah, definitely. And my question was about I know that in the NISQ model, you are interested in measuring the qubits that are related to the sentence category, and you use post-selection in the rest of the qubits.
Yeah, okay. So and this was an initial, what you say, I would say, to make stuff easy. I mean, I don't know, you know, but then every time if people do teleportation experiments, they also use post-selection historically, because but now there's a few tricks we're doing now to avoid them. So we're slightly changing the grammatical structure. We're doing experiments with new. So it's the way how you represent the diagram at a circuit, and there's different options there. There actually hasn't been that much work published on how you optimally do that with the least possible post-selection, if possible, none. So and you can get away with much less than we were doing, and we've been shown. Now there's of course complete alternatives, and that's, for example, going to sort of some measurement-based quantum computing paradigm where you correct for the wrong post selections. And this is the sort of model that the optical quantum computing people are implementing, like PsiQuantum and all that. So we're specifically also very putting a lot of effort in looking at those, because then you're and I mean, in a way, language may. I mean, I'm thinking about this, but I think language may more naturally fit on a sort of measurement-based architecture than it does on a circuit architecture. Then, yeah, I mean, I've got some good hunches there. But anyway, we're trying all architectures, of course. And at the moment, there aren't any optical quantum computers. They don't exist. So we're working with a chip in a lab in Vienna, an optical chip, but this is still like sort of lab experiments, and it's a completely different beast than sticking something on a quantum computer.
Okay, I think we're running out of time. Venkatesh, can you?
Excellent. Yeah, that was a very interesting discussion, and thank you very much for all of you to engage in the question and answers as well. And thanks very much, Rob and Antonio, for making it so interactive. So if that's all right with everyone, we'd like to close this webinar session. Thank you very much. And upcoming in the series are 2 more, one based on quantum approaches to rule-based systems, and another one on quantum approaches to probabilistic safety assessment systems. So thank you very much. We look forward to you getting back to us.
Thank you.
Thank
Bye-bye.
you.
Thank you. Bye.